Welcome back to our coverage of general statistics. In this lecture, we're going to look at sample surveys and discuss some pertinent issues in sampling. All complicated phenomena can be explained by simpler scientific principles. I agree with Linus Pauling here. You might be thinking, are these principles we're doing all this statistics? That's the simpler scientific principles? Yes, in fact it is, because as complex as this is, it's still simpler than the incredible complexity that we see in social behavior of humans or even animals. This cat here, this is not the mother cat. This is just my cat who loves these kittens. Look at that, these baby kittens with their sophisticated social behavior. As you can see, there's clear bonding and relationships there. They're less than a month old and yet exhibit this extraordinarily complex social behavior that is just has a very simple representation relative to the kinds of incredible complexity that we observe in everyday phenomena in human behavior and in population, human population behavior writ large, not to mention the incredible complexity observed in the human body. So we need to break it down because as scientists, we want to explain social phenomena, health phenomena, but how do we do that? The tools are really here, and they are statistics. And as part of statistics, we need to be cognizant of sampling and research methodology, because all the statistics in the world cannot save you from if you've used bad methodology. So in a way, sampling is one of our most important topics. Certainly, when you're applying these ideas in the real world, it's incredibly important to understand. To get into thinking about sampling, let's first look at some vocabulary, and as it pertains especially to this idea of estimating parameters. First, let's define some terms. A sample is part of a population. A population is a group that you've defined. So we could say, for example, our population is children living in the city of Flint who've been exposed to lead-contaminated water. That's a large population. We've defined it in a specific way. I could be more specific about the population and say I wanted to look at children under 10. You can define your population in very explicit terms, and that's an important point because when we take a sample from a population, we have to have already defined the population clearly, and incredibly important to remember that your population is the population is defined by the researcher, not by external factors like the US population, unless it's the population of interest. So a sample comes from the population. It's literally people who are part of the population or other observations that are part of our population. Here we have next the idea of a parameter. A parameter is a numerical fact about a population. This parameter can't be determined exactly. It can only be estimated. And many of our statistical procedures are in the effort of doing just that, to estimate parameters about a population based on the sample. So we need to be able to describe our sample appropriately. A statistic is something that's computed from a sample and used to estimate a parameter. So a parameter and a statistic are different things. A statistic is what the investigator knows. This statistic is based on the data. A parameter is what the investigator wants to know. We're trying to get accurate statistics so that we can have, or valid statistics so that we have accurate parameters. And when estimating a parameter, it's important to think about the major issue of accuracy. How close is the estimate going to be? And this is something we will think about in some conceptual terms today. It's safe to estimate the parameter from the sample when the sample represents the population. It's impossible to check just by looking at the sample. The reason to see whether the sample is like the excuse me, to see whether the sample is like the population in ways that matter, investigators have to know facts already about the population, and we don't already know those facts. If we knew them, we wouldn't necessarily need the sample. So we've got a vicious circle here. So we have to think about what's happening when we're sampling and how does it affect our estimations of parameters. The two main lessons here are that the method of choosing the sample matters a lot. Your sampling methodology is really incredibly important. And the best methods involve the planned introduction of chance or randomization, is another way to conceptualize chance. Let's think about bias. We have two possible kinds of bias that are primarily addressed in this chapter: selection bias and non-response bias. When a selection procedure is biased, taking a large sample doesn't help because this just repeats the basic mistake on a larger scale. How could you get selection bias? Well, it's very easy. Any methodology that uses investigator choices and judgment is always going to result in selection bias. This is why randomization is so important, and we'll see it illustrated in a couple of examples. Let's also think about our other kind of bias. But before we do, just a brief example about selection bias, because you might be thinking, well, what if the investigator is aware of the problem of bias, and so they want to, and and this is of course not one of us, but an investigator without a proper grounding in statistics might be thinking, I'd like to, I'm aware of bias, so I'd like to address it in sampling. Now, there are ways you can address bias probabilistically, which we'll look at shortly. But if we think about bias in this loose kind of way that some investigators you might say, well, an investigator might be very concerned about racial bias in sampling. And so let's say we were doing a sample, we're doing a study of breast cancer, and we were working in a clinic. And so we wanted to sample women coming in for mammograms and the population is women who show some risk in their mammogram output. And so we sample from that population and think just on a non-probabilistic way, well, I know there's racial bias, or maybe there's a higher risk associated with certain racial subgroups. Then they might, quiet. Then an investigator might say, well, then I'd like to address that by including every Black woman that comes through. Stop doing that. Sorry. An investigator might say, well, I know there's bias and there's a problem of underrepresentation of Black women in breast cancer research. So I'm going to include every Black woman. Well, this is its own kind of selection bias, because then the Black women who come into the clinic are not being sampled randomly for selection into the study. They're just being included because they're there. But the other portion of our population, let's say just looking at white and Black participants, our white participants might be subjected to a different sampling procedure whereby they only get in when where they're actually sampled on a random basis or something approximating it. I mean, there's lots of examples of selection bias, but one that gets really tricky for people is thinking about race, because they often want to address racial bias in ways that aren't really appropriate. So if we want to actually address an issue of selection bias in the race of our participants, we can't have different, we can probabilistically sample them, as we'll discuss later, but we have to establish clear rules for how people get into the study, even if we have different rules for different subgroups. And then once those rules are met, random chance needs to determine which participants from those available who meet the criteria, which participants make it into the study. The process must be random, as we'll see. Our other kind of bias here is non-response bias. In short, non-responders can be very different from responders. When there's a high non-response rate, you have to look out for non-response bias. For example, those people who are not at home when an interviewer calls may be different from people who are at work, especially with, or might be different from people who are not at home with respect to things like working hours, family ties, social background, and therefore attitudes of interest. So if you want to appraise a sample, ask yourself, what's the population here and what's the parameter? It's also important to know clearly how was the sample chosen? Oh my gosh, I'm sorry. It's a chaos over here. And so when you're appraising a sample, we have these core set of questions you should always be aware of. Where does your sample come from? What is the population? You must be able to clearly define it. What's the parameter of interest? You should know your parameter clearly defined. Key, and this is essential here to addressing and being aware of selection bias, how was the sample chosen? And what was the response rate? If you don't have a good response rate, then the data might not be valid. Good survey organizations keep these problems in mind and have really ingenious methods for dealing with them, as we'll see. Our book goes into some a nice example about the year the polls elected Dewey, but we're probably all echoing. You can see that some of the same ideas were echoed in our election in the past year. Okay. Go. Go, you too. As you know, most of you, I'm sure, preceding the recent election, Hillary Clinton was heavily favored to win. There were tons of polls, and they all predicted she was going to win the election. The polls elected Hillary Clinton, but the population elected President Donald Trump. Now, given that there are issues that are not sampling related necessarily to what happened in our recent election, what I'm referring to is that we don't fully know yet what the repercussions of the Russian hacking into the election. So we can't say whether the issues with the polls and whether the issues in the recent election were with the polls or somewhere else. It's certainly true that we've seen this kind of trend in other, we've seen it in other elections too. And why are polls off like this sometimes? Well, it's frequent that a quota sampling procedure is used. And in quota sampling, the sample is handpicked by the interviewers to resemble the population in some key ways, some ways that the researchers have decided are essential to representing them, to getting representing the distribution on certain demographic variables. But the problem is that a perfect cross-section on all demographic variables may not result in a representative distribution on the variable of interest. Because if we already knew how all of those demographic variables, if we had perfect predictions for them on the variable of interest, then we wouldn't need to do the sampling at all. So there's real problems with quota sampling, but another really important major problem with quota sampling is that within the quotas, interviewers are free to choose anybody they like. And anytime there's judgment or choice in the selection process, judgment or choice on the part of the researchers, that introduces selection bias. How can we address these problems with quota sampling, which on the surface seems like a good procedure? Well, we need to use chance in our survey work. And there are a variety of probability methods for sampling. The point is that there's an objective chance process to pick the sample. No discretion can be left to the interviewer because it will inevitably introduce selection bias. The hallmark of a probabilistic method is that the investigator could compute the chance that any particular individuals in the population will be selected for the sample. Why could they be able to compute the chance? Because of the random selection procedure. We already know that there are specific rules that apply to a chance process or a random process. And so if we utilize a random process in our sampling, then we can use these very useful mathematical tools and statistical rules that apply to the chance process. And our probability methods guard against bias because blind chance is impartial. We'll look next at one basic probability method, simple random sampling. In this case, we draw subjects at random without replacement, and simple random sampling is very effective. It's easy to implement simple random sampling on a smaller scale, like in the example we discussed earlier, where we are working in a clinic and hoping and have a population of interest as women who have mammogram that shows some risk. Simple random sampling in this scenario would predict that we would have outlined an algorithm for inclusion of participants in the sample. So we'd have rules like risk needs to be quantified in a specific way, and any women who meet that criteria are available for inclusion in the study. In a clinical method, simple random sampling is often accomplished by an algorithm set out where every so many women who come in, every so many qualified participants are sampled into the study. It's still random because the participants come in, or the patients come in a generally randomly distributed way. So thinking about these probability methods, we need to consider how well they work. Well, they do a pretty good job at minimizing bias. Impartial, objective probability methods, when used in sampling procedures, are pretty good at eliminating selection bias. And selection bias is a real danger. We have other ways of dealing with non-response bias, but selection bias is the biggest danger to good study design. Remember that judgment and choice inevitably show bias. They always show bias. Even when someone is very informed and trying not to show bias, you're still showing bias. You can't get away from it. This is why we have all these methods to help us better address this problem. Chance is impartial, and it offers us some great associated, powerful statistical techniques. So our estimate for our sample is our estimate for, excuse me, based on a sample is going to be equal to always the parameter plus whatever bias is in the sampling process and chance error, which is always present. So we know we can minimize bias, but chance error is always there. Chance error is also called sampling error. And as we've discussed, any random process has random error or chance error. We call it sampling error. Bias is called non-sampling error because it's comes from the investigator or the participant in terms of non-response bias. The error in that sense is not housed in the sampling procedure as it is in chance error, where the sampling error is part and parcel of the chance process. Instead, when we're talking about bias, it's always referring to non-sampling error, which can be minimized through the use of good research methodology and study design. As we learned in this chapter, it's important to take into consideration how error, whether it's chance error, but especially bias, is likely to be affecting your population. Sometimes students think that with a simple random sample, the sample percentage is likely to equal the population percentage. However, this there's because of the constant presence of chance error, we can only ever estimate our population parameter within a certain margin, accounting for our, when we include our estimations of chance error. In real sample surveys, we use methods that are much more complicated than simple random sampling. And we see that illustrated nicely in the GSS survey, the global or the general social survey that we've been working in lab, where they use complex multi-stage sampling. And if you'd like to learn more about complex sampling procedures and some interesting examples of how that is played out in these large population surveys that are used quite frequently, take a look at Chapter 22. So some take-home ideas here to remember are that the method used to draw the sample matters. Some methods are terrible. Handpicking the sample to get a representative cross-section, it doesn't work out very well. Haphazard selection, maybe even worse. And the best method for drawing a sample involves the planned introduction of chance. Some of you may recognize this quote from other contexts, but it is used in your chapter discussion. So if you haven't read the chapter yet, you can look forward to this example and discussion of the polls. In our next section, we'll take a look at some of the review exercises and get a good idea of what to do with and how to account for some of the bias problems that we've discussed today.